In the last video, we discussed measures of center, and in this video I want to discuss measures of variation. Now, by far the most important statistical characteristic in the last video was the mean, the arithmetic mean. In this video, what I want you to take away from this video is, everything that we're going to cover is important, but the standard deviation stands out as the most important statistical quantity that we're going to cover in this set of notes. So in general, in terms of measures of variation, we're going to talk about four different classifications or characterizations of variation. Now, in general, variation gives you some insight or some information about the spread of the data, or how the data is dispersed relative to its center. So we're going to talk about the range, the variance, the standard deviation, and finally the coefficient of variation. Now, before we get started, we're going to use the same rounding rule that we used with measures of center, and that's to use one more decimal place than your original data. So nothing changes. It's always one more. With descriptive statistics, it's one more decimal place than your original data. Now, the first measure of center is also the most basic measure of center, and that's the range. And the range is simply how far apart is the smallest and largest number in your set. So it's the distance between the maximum and the minimum, or the range is equal to the maximum value minus the minimum value. So in this set here, represented by a dot plot, there's a 1, that's the smallest number. There's a 13, that's the largest number. So the range is the difference between them, or 13 minus 1, which is 12. Now, one thing to note about the range is that it doesn't tell you very much about the set. It doesn't tell you anything about how the data is distributed or any patterns inherent to the set. It simply tells you how far apart is the smallest and largest values. All right, so that's it for the range. There's not much to talk about there. Now I want to talk about the standard deviation. This is a really important topic in statistics. We're going to use the standard deviation throughout the remaining, well, basically, within every topic from here through till we stop talking about statistics. Standard deviation is going to be part of the discussion. So the standard deviation, it's denoted by S, or at least for the sample standard deviation is denoted by S. And it's a measure of the variation of values, of individual values apart from the mean. So we're using the mean as the center of the set. And the next two statistics that we're going to be talking about, the standard deviation and the variance, are very, very closely related. And the standard deviation is actually the square root of the variance. And so what we're basically doing with the standard deviation is, if we look at the number line, and let's say you have the mean of some data set here, and you have, I don't know, the first x value is here, and the second x value is here. Let's say there's just two numbers in your set. Well, yeah, actually, let's say, I don't know, this is x1 equals 4 and x2 equals 6. And so the mean, or the average of 4 and 6, would be 5. So if we look at the difference, or the deviation of each x value from the mean. So this first x value has a deviation of -1. It's 1 unit below the mean. And x2 is 1 unit above the mean. And so if you take the average of -1 and +1, you get 0. So if we look at the average deviation, we get 0, which doesn't really make sense, because there is deviation here. The first x value is below the mean. There's a deviation there. And the second x value is above the mean. There's a deviation there. So we can't look at the actual deviation. What we're actually going to do is look at the squares of the deviation. So if we take a distance, so if the distance above is positive and the distance below is negative, if we square that deviation, If we square a positive number, it's positive. If we square a negative number, it's also positive. So the standard deviation is going to be approximately equal to, not exactly, but approximately equal to the average of the squared deviations about the mean. And then we take the square root of that number. Okay, so here's the standard deviation. Here is, for each x value, we look at the distance between that, like, first x value minus the average, square it. Second x value minus the average, square it. Third x value minus the average, square it. Now, the reason I say it's the approximate average is because, well, if there's 10 numbers, we don't add up those 10 numbers and divide by 10. We add up those 10 numbers and divide by 9. We divide by n minus 1 for the sample standard deviation. And I'll have a separate video with a discussion on why we use n minus 1 instead of n. But with the population standard deviation, so this is sample, this is population. The population standard deviation is exactly the average, or the square root of the average of those squared deviations from the mean, because in the population version we're dividing by n, but in the sample version we're dividing by n minus 1. The one in blue here, this is the one you're going to be calculating 99% of the time in a statistics course. It's the most commonly used measure of variation, and it shows, it's basically a way to quantify the level of variation within a data set. So the higher the standard deviation, the more spread out the numbers are. That's it. That is standard deviation. It's a measure of how varied the numbers are, and larger standard deviations mean larger variation. Now, there's a drawback with the standard deviation, and that is it is a biased estimator. And what I mean by biased estimator is that, in our previous discussion about sample statistics and population parameters, we talked about using sample statistics and calculating those sample statistics to estimate the value of population parameters, because normally the population is too big to work with, so we work with the sample. Now, what I mean by a biased estimator is that if you take a bunch of samples and you take the standard deviation of each of those samples, so sample 1, standard deviation 1. Sample 2, standard deviation 2. Sample 3, standard deviation 3, and so on. So you have a number of samples and a number of sample standard deviations. If you average out those standard deviations, they don't get closer and closer to the value of the population standard deviation. So we say the standard deviation is a biased estimator, because if you have a bunch of these, if you have a bunch of sample standard deviations, doing so does not get you closer and closer to the population standard deviation. Now, this is a topic that we'll look into in detail later on in inferential statistics, but that's still a little bit of a ways off. So at this point, all we could say is something is or isn't biased. And at this point, we have to leave it at that. And so the standard deviation is a biased estimator. Now, without the square root, what we calculate is the variance. So the variance is the square of the standard deviation. So standard deviation squared will give you the variance, or the square root of the variance will give you the standard deviation. If you have one, you have the other. If you have the standard deviation, you could square it to get the variance, and if you have the variance, you could square root it to get the standard deviation. Now, the variance is an unbiased estimator, meaning the variance, if you have a bunch of sample variances, they target the population variance. So the variance is useful in the context of inferential statistics. But the problem with the variance is the units. They don't make sense. Since the standard deviation, or since the variance is equal to the standard deviation squared, what happens is your units are squared. So if your original data is measured in inches, your standard deviation is measured in inches, your mean is measured in inches, your median is measured in inches, your mode is measured in inches. All the characteristics of that set are measured in inches, except the variance. The variance is the square of the standard deviation. So if your data is inches, your variance is square inches, which doesn't align with the original data set. But, I mean, there is a such thing as a square inch. Now, if your original data set is measured in dollars, then your standard deviation and your mean and your median and so on, they're all measured in dollars. But your variance is measured in square dollars. And there's no such thing as a squared dollar. So sometimes, I mean, always the units of your variance don't align with the original data set. And sometimes the units of the variance they don't make any sense. So we do not use the variance to describe data. We do not use the variance in the context of descriptive statistics. All right, so I say here, caution, the units of the variance are different from the units of the original data. Okay, and so that's basically it. Our formulas for variance and for standard deviation. And I have a separate video where I show on Excel how to calculate each of these. Now, we have different formulas. So in the sample version of both the variance and the standard deviation, we're dividing by n-1. And in the standard deviation, there's a square root, but still dividing by n-1. And in the population version, we're dividing by n. So we get two slightly different numbers. So if we're using Excel, we have to have two separate different formulas for the variance and two different formulas for the standard deviation. So let's say sample population, standard deviation, and variance. All right, so in Excel, the function name for standard deviation is STDEV. STDEV. And the way to distinguish between the two, or the way to tell Excel whether you're working with the sample or the population, is with a .s or a .p. .s mean, and then open the parentheses, and then the data goes in there. So .s and .p stand for sample version and population version. And then with the variance is the same thing. The Excel function for variance is var, and there's a .s version, which is this one, and there's a .p version, which is this one. All right, so it's important to keep those two straight. And in general, if we look at sort of this idea of variation or spread of a data set visually, the more dispersed the data set, the larger the standard deviation. And not just the standard deviation, also the variance. So larger standard deviation here, the data is more spread out. Smaller standard deviation here, the data is closer in terms of like being close to the mean, the data is closely packed to the mean when the standard deviation is larger. Now, we're going to be using the standard deviation and the mean. Those are the two sample statistics that we're going to be using more than anything else by far. And one thing I want to point out is there's no correlation. Well, I don't want to use the word correlation yet. We haven't defined it. But there's no relationship between the mean and the standard deviation. So here's an example of 3 data sets that all have the same mean, 15.5, 15.5, and 15.5. So the values in this first set are 11, 12, 13, 16, 16, 17, 18, and 21. That's a mean of 15.5. In the second set, 14, 15, 15, 15, 16, 16, 16, 17 also has a mean of 15.5. Same with set C. But they all have different standard deviations. So just because 2 sets have the same mean doesn't tell you anything about their individual standard deviations. All right, and so just to summarize the characteristics of variation, and by variation I'm talking about the range, the standard deviation, the coefficient of variation, and so on. The more the data is spread out, the larger the values of these 3, the range, the variance, and the standard deviation. And on the flip side, the more the data is concentrated, the smaller the values of those 3. The variation, or the standard deviation, and the variance will always be, well, let's say never be negative. They'll always be non-negative. Almost always they'll be positive. The only way to have the range, the variance, or the standard deviation, the only way to have any of those equal to 0 is if you have a set consisting of only one number repeated. So there's 6 copies of the number 4. There's no variation there. The range is 0, the variance is 0, and the standard deviation is 0. So it's impossible to be negative. It can be 0 if you have only one number repeated. And other than this one specific trivial case, those numbers will always be positive. Okay, one thing I mentioned on my last video in measures of center was to have sort of a key with a list of all the symbols that we've established so far. And so we have 2 symbols. Let me use actually a different color here. We have 2 symbols for the mean, one for the sample version, one for the population version. 2 symbols for the standard deviation, again, one for the sample, one for the population, and 2 symbols for the variance. Again, one for the sample variance, one for the population variance. So we have 2 symbols for most of these statistical quantities, one for the sample statistic and one for the population parameter. Now it's really important that you're familiar with and keep these symbols straight, because we're going to be establishing quite a few statistical formulas, and they're usually given symbolically. All right, so one question I want to ask about the variation, and so the word variation refers to both the standard deviation and the variance. And so let's say you have 2 sets. One set has a range of 100. So let's say one set, I don't know, is somewhere between 26 and 126. And so all the numbers are in here. I just chose those numbers at random. And another set has a range of 50. So, I don't know, let's say 45 to 95. So the other set is, well, I don't want to say it's on the same number line. That's being too specific. So let's say, oh no, you know what, that's fine. We could do that. 45 to 95. Yeah, that's fine. So you have one set where all the numbers are spread out between the 26 and the 126, and the other set where all the numbers are spread out between the 45, the 45 and the 95. Now, which of these two sets has the greatest variation? They're both measured in the same units. They're both measured in pounds. So one set has a bunch of data values ranging between 26 and 126 pounds. The other set has values ranging between 45 and 95. Which one has the greater variation? Well, intuitively, you might say set A, because the numbers are spread out twice as much. But, in fact, that's not the case at all. So what if I were to say that set A consists of a set of weights from 10 blue whales, where a blue whale, on average, well, I don't know what the average weight is, but they could grow up to 400,000 pounds. And set B is a set of weights from 10 dogs, where dogs are usually, I don't know, less than maybe 200 pounds would be like maybe a pretty darn large dog. So 100 pounds in the context of blue whales is nothing. If you have 10 blue whales that are all within 100 pounds of each other, then they're all pretty much identical. If they're all within 100 pounds, they're all pretty much the exact same size. But if you have 10 dogs all within 50 pounds, well, there's a huge difference between a 10-pound dog and a 60-pound dog. So 100 pounds in the context of whales is a tiny number, but 50 pounds in the context of dogs is a huge number. So the way we deal with this comparison between two data sets, if we want to compare the variation between two data sets, we can't just look at the raw numbers. We can't just look at the standard deviation itself. We have to look at what's called the coefficient of variation. So what we do is we basically normalize the standard deviation. And if we look at two sets with two standard deviations, we don't compare the standard deviations to each other. We compare the standard deviations relative to their individual sample means. So what we do is we take the standard deviation of the set and we divide it by the sample mean. And we write this as a percentage, so we times it by 100. And so I have a separate video where I work through a problem where we're using the coefficient of variation. So after this video, that's probably a good one to watch. Okay, so now that's it. We've talked about the four measures of variation: the range, the standard deviation, the variance, and finally the coefficient of variation. Now, the last thing I want to do, and there's only a couple of slides left, the last thing I want to do is talk about a few estimations that we could employ that sometimes will allow us to answer a question quickly if precision isn't a top priority. So, and there's three of them, and there's 3 slides left in this set of notes. We have the range rule of thumb. Now, the range rule of thumb is how we identify what are called unusual values. And we define unusual in terms of standard deviations. So, the term unusual referring to a specific data value. A specific value is unusual if it's more than 2 standard deviations away from the mean. So either 2 or more above or 2 or more below. Okay, the next estimation is called the empirical rule. And the empirical rule says if your data is bell-shaped, if your data is bell-shaped, then approximately 95% of the numbers in your set will be usual and 5% will be unusual. And if we could also extend that to plus or minus 3 standard deviations, and then it says that 99.7% of your set will fall within 3 standard deviations. But we're going to be relying on this one much more often. And finally, so this empirical rule is only for bell-shaped data or normally distributed data, which we'll talk about later. And finally, if you don't know this, if you don't know your data is bell-shaped, then Chebychevs Rule says that for any distribution of data, not just bell-shaped, but for any distribution of data, at least this much of your data, this percent, which is 1 minus 1 over k squared, this percent of data will fall within k standard deviations. So if you plug in 2 for k, you get 75%. If you plug in 3 for k, you get just under 90%. But again, these are approximations. These are estimations that we're not really going to use very often, but it's a general rule of thumb as far as a first glance or a quick estimation. Okay, so that about does it for measures of variation. From here, I think the best thing to do would be to watch my videos on using Excel to calculate the standard deviation, the variance, and the coefficient of variation.